my name is Sylvia, and I'm presenting my dissertation on visualizing monitoring data through BIM. And this is a brief summary of the content of this presentation, which starts from introducing the basic concepts, and then it takes up until the integration of BIM with IoT, and then the methods used and the final conclusion. Introducing it, so visualizing monitoring data through BIM, the objective was to improve the overall efficiency of facility management and then integrate real-time or historical data from sensors into the BIM model, and then also develop a decision-making dashboard in comparison with benchmark standards. This work was developed in collaboration with Francofa Italia. Not to waste so much time, because previous speakers have already introduced these basic concepts, so the idea is to explore the advantages of BIM used in facility management, which are the operations or activities carried out during the life cycle of the building. So to implement BIM with facility management, this is done through digital. First of all, before we go into what digital twin is just to understand the overall concept of digital transformation, which is also known as Industry 4.0, and where the Internet of Things is the main driver of so many other technologies involved in this transformation. So integrating BIM with IoT results in the creation of digital twins. So about the concept of digital twins, the most advanced sector currently using digital twins in the manufacturing sector, which they'll propose a process for creating a digital twin, which the main elements of a digital twin has to do with the physical world, the digital world, and the integration, the bidirectional flow of data and information between these two spaces. So it starts by putting sensors in the physical space. These sensors collect data, which are then transferred into the digital space. The data is analyzed by algorithms, and then this data can also be translated back through actuators into the physical space. So to integrate BIM with IoT integration, this takes advantage of the geometric and parametric properties of a BIM model and adds it with real-time sensor data. This helps to create a digital twin. So I did a few research based on literature review and existing workflows to carry out this integration. And here shows some of the software identified and as well as the workflow summarized from the literature review. So going through the workflow, this is one workflow which summarizes the steps. This one uses the data from the sensor database through Dynamo, and then the model, the visualization of monitoring data is done in Revit. And in this case, the sensor data is collected in Dynamo. Another workflow here covers two workflows, which works with Navis work. In this case, the visualization is done in Navis work, and an alternative workflow is using an addition of an API, which also adds additional feature, and this is visualizing Navis work. After this, comparing all these three summarized existing workflows, the third one, which uses the integration of API, seems to be the most functional because it covers visualization in 2D, 3D, and you can view historical data and other information of the building. However, for my research, the target user is a facility manager, which only needs the model to visualize, it's not a BIM author, doesn't need so many functionalities that the BIM model comes with. Therefore, it was important to find an alternative solution. And in this case, a possible solution could be a cloud-based platform that has APIs that can be used and also adheres to open BIM standards. So the model doesn't have to rely on proprietary formats like RVT, ArchiCAD, so it can be used with open BIM standards like IFC. So introducing what cloud-based digital twin, it's basically, so far now it's having a lot of rise. So the cloud-based services can be defined in three different stacks, which goes from the infrastructure to the platform and to the software. And each of the stacks provide different levels of control and flexibility. So an example of a cloud-based platform in this case is the Autodesk Forge, which provides a platform, and it's a platform as a service. So it gives the developers the ability to create and work on their platforms. So to implement this integration, it was implemented in 2 phases. The first phase introduces the case study building down to the platform use, and the second phase is the implementation. And this follows the steps summarized from the literature review. As we go forward, we would go into the framework. So for the first phase, this is the case study applied, which is an existing school building in North Italy. And the implementation domains used was the environment quality, indoor environment quality, and the indoor thermal comfort. And on the table here, we can see the parameters visualized and monitored in the field. So from the visualization platform, it provides a set of APIs, and the APIs we focused on was the data visualization and the viewer API. So for the data visualization API, which was recently released a few months ago in May, they released a default reference application that is used as an IoT toolkit to integrate IoT sensors into a BIM model. And to get started, you need to create a Forge account. You need to install some languages or some packages on your computer, and as well, you have to have a basic knowledge of the Forge API. So to get started, I first of all had to go through the Forge API to have a good understanding of it. So in the Forge API, it's just a 3D viewer, and you can upload or view over 60 different formats, including vendor neutral formats like IFC. And this, so for this implementation, this is a sample model was used to go through this tutorial. And also you can see it was mostly developed in the back end through an IDE, which was Visual Studio Code and a Node.js programming language. And then this was deployed on the internet through Roku. And then here shows the implementation of the so here shows the implementation, the web app developed on the that was deployed on the browser. So you can also scan this if you would like to explore this. So this show the potential that the web app, the Forge viewer, can be used to create a web app. So going into the second phase of the implementation, so we start with the data acquisition of to collect the data. So here the data was the acquisition was through the Revit model and the data sensor database. So the sensor database used in this case was through the Influx database and was graphically viewed in Grafana. And here is a summary of the sensor parameters visualized in the model. So to implement this, a family had to be created in Revit, and then a unique identifier, which was the sensor name, was used to map this parameter. And then this family was placed in the BIM model at different instances in the building. The second step was the integration, which had to do with mapping this data within the BIM, within the Forge, the integrated development area, which is the Visual Studio, mapping the position of the sensors in the building and the property names. Another step was to define the device model of the parameters used, define the gradient maps and the different icons to represent it. And also to add the sensor data, it's possible to add your real-time data, which was connected through Influx database. And you can also add, use a CSV file to connect to your historical data. However, you have to follow certain formats for your CSV, like the naming, the heading, and then also the name of the CSV file has to be named according to your sensor, so it's possible to map this data. So going into the integration, so this was done in the, this is the final, the look of the integration in the, using the reference application, where you can see the gradient maps up in the rooms according to the gradient maps defined of each parameter. Also, while in the viewer, it made it possible to identify sensors within the viewer that have not collected data for a long time because the connection is in real time. So checking the viewer where you see in a certain time, you'll be checking the database as well. These sensors didn't collect it. So this part talks about the data analysis, which is the main contribution of this research. Here, a decision-making dashboard was used with reference to green standards, and this identified the threshold parameters for each monitored sensor, and a dashboard was created. So here you can see it falls under 3 different ranges where you have the low, the comfortable, and the high. So this is used to understand and interpret the data collected from these sensors to make sense and to be able to make in-time decisions. Finally, this is the digital twin implemented. You can see in the video, you can, through the interface, you can select the sensor, you can see the graphical view of the sensors, and you can select which data you would like to visualize. And with that, the dashboard also changes according to the data selected. You can pick different timestamp. In the viewer, you can see how the data changes. So as you play, you can see the heat map changing and the sensor dimensions change. Okay, so in conclusion, along with the benefits of this framework, I also identified a few limitations which had to do with poor performance and dependency, lack of sufficient resources, and high level of programming. And some of the processes had to be hard-coded. So also to further make the process efficient, I had some suggestion for future research, which is adding actuators, which are devices that can take this monitored data and send back, instigate actions in the physical space, where assuming the temperature of a space is higher than the comfortable threshold, the window can maybe mechanically open on its own or get closed or reduce the occupancy of the space. Data analytics, possibility of integrating this platform with analytic Power BI tools like Power BI and also advanced visualization. And I think that's it. And so far, thank you. And that's all.